Hello everyone, welcome back to Electronics 1. Last class we looked into explaining how a bipolar junction transistor works in the forward active mode, all while assuming that no recombination occurs in the base and therefore no current flows into the base. And although it may not have been clear at the time that was the assumption that we were making, but now anyone that has used a bipolar junction transistor will know that the base current is in fact not zero. And let's talk about the origins of that base current. Okay, so in our derivation of collector current, we made two assumptions. And those were that there was no recombination in the base, so none of those minority carriers combined with majority carriers. And although we talked about it a bit at the beginning of the lecture, we basically neglected any majority carrier diffusion from the base to emitter. We said that the majority of the current flowing across that junction was due to diffusion from emitter to base. Okay, but the majority carrier diffusion from base to emitter we assume to be negligible due to the light doping of the base and that assumption that the majority carrier concentration was not sufficient to result in any substantial diffusion. Okay, so let's revisit these. So let's talk about base recombination. Okay, so if recombination does take place in the base, then that concentration gradient is no longer linear. Concentration gradient of injected minority carriers is no longer linear. Okay, so if we look at the diagram again of the concentration gradient in that base region, this is what the assumption we made for our discussion last class. So this is the case with linear. This is assuming no recombinations occurring. When in reality there's going to be some recombination, and we're going to get a concentration gradient that is not linear due to recombination. Okay, what's the impact of this recombination, even if it is small? This is, causes a loss of both minority carriers, those in this example, those electrons that were injected from the emitter, and it causes a loss in majority carriers. The holes in that base, again in this example we're assuming the base is p-type, those holes that recombine with the electrons are also lost. So if we try to represent this recombination and this loss of minority and majority carriers kind of graphically here, okay, so if this is my base region in the middle, and if we assume that this is an NPN transistor, so this is n-type, my base is p-type, the collector is n-type, and with this this diffusion of minority carriers, or these injected minority carriers, if one of these electrons ends up recombining with a hole, here we have this loss that I've talked about up here above, loss of both minority and majority carriers. Okay, in order to account for those lost carriers, they have to be replenished from the external circuit. So my base ends up contributing the lost hole, the lost majority carrier that existed in the base, and my emitter circuit, external circuit, needs to contribute that lost electron. Okay, so in both of these cases, these are coming from the external circuit. Okay, so in an NPN transistor, the loss of an injected electron makes the emitter current slightly greater than the collector current. Right, because this extra electron that I'm depicting in this diagram, this is an electron that's coming in that has no association with the current flow into the collector. This injected electron is purely to counteract this this recombination that occurs, that is counteracted from the emitter through an ejected electron and from the base with an injected hole. Okay, so that results in a slightly larger emitter current than the collector current. As this electron has to be made up from the external circuit, or provide it from the external circuit. Okay, and we can make a similar argument for the hole lost in the base due to recombination. This has to also be, made up from the external circuit. Okay, so, or in other words, current must flow into the base. Okay, and this is all a result of this recombination occurring in the base region. Okay, but the other effect here that we ignored to date is diffusion from base to emitter. So we looked at diffusion from emitter to base, but we didn't consider any diffusion of majority carriers, those holes from the base to the emitter. Okay, so although the base is only lightly doped, there still exists a concentration gradient between the base and the emitter. So the concentration of majority carriers is greater than the minority carriers concentration in the emitter. So we still will get diffusion current from the base to the emitter. In the case of our PNP transistor, those majority carriers, which are holes in the base, the concentration of those still exceed the concentration of the minority carriers, or the holes in the emitter, and hence we still will have diffusion. Okay, so quick look at this again. This being our base, assuming an NPN transistor again. So this is N, this is P, this is N. We are going to get, due to there being a higher concentration of holes in the base, those are going to diffuse across this forward bias junction. So there is going to be a diffusion current from base to emitter as well. And again, the loss of this hole in the base is going to need to be replenished from the external circuit. So this is another reason why we're going to get some current flowing into the base. Okay, so the reverse bias junction BC, this junction, prevents diffusion. So we don't get any diffusion current into the collector. However, the forward bias of the base to emitter junction, this junction here, does allow some diffusion. Into the emitter. And again, if we specific reference to an NPN device, and we can make all these same arguments for a PNP as well, and just we'll be talking about the opposite charge carrier. And in an NPN device, the resulting loss in holes in the base must be replenished through the external circuit. And again here, this is why we have current flowing into the base. Another reason why we have current flowing into the base. This is represented in figure 6.3 of Cedar-Smith. We see that we have this base current due to recombination. So some of these electrons are that were injected from here didn't make their way to the collector. Okay, so that this, you'll note kind of the, you look at the width of this. This is why it's depicting that the emitter current is slightly larger than the collector current due to this these electrons that are recombined with holes in the base. Okay, so that is contributing to a little bit of base current. They've called IB2 here, and then this last thing we talked about, this diffusion current that happens across this forward bias base to emitter junction, that results in some additional base current that they've depicted as IB1 in this diagram. The sum of those two currents result in a base, a current flowing into the base. Okay, so if we return now to our schematic symbol for our NPN transistor, we can now appreciate that there is some current flowing into the base. There is current flowing into the collector. Again, notice I'm going with the direction of conventional current flow, so just be careful here. The current flow that we've been talking about has all been the flow of electrons, and we remember that flow of electrons is opposite to the flow of conventional current. Okay, and we have some current flowing in the emitter as well. Make this a capital E here, and you know, our Kirchhoff's current laws still need to apply for a transistor. So it's really a conservation of energy law that says the current in must equal the current out. So here the base current plus the collector current must be equal to the emitter current. And if we acknowledge that the base current is small, we can often use the assumption that the collector current is approximately equal to the emitter current. Okay, and as I said, all of these same things apply for a PNP device as well. We just swap the direction of current flow. Well, in fact, it's not just the base, the emitter and collector current flow directions are also swapped. Oops, let me get my figure right here. It's easy to know the direction of current flow in the emitter here. The emitter is always the terminal that has the arrow on it, and the arrow depicts the direction of current flow. So we'll notice that emitter current is now flowing into the device, collector current is now flowing out, but the base current is also flowing out because, well, now our base is N-type, so yes, electrons are flowing into the base, but electron current flow is the opposite direction of conventional current. Okay, so hence our directions. Okay, but from this we can see that the same relationship exists between the currents. And that is that the emitter current is equal to the base current plus the collector current. Okay, so we have some parameters to define these the relationships between these various currents. So while we said that our collector current and our emitter current are approximately equal, they're not precisely, and we use the letter Greek letter alpha to define the difference between the collector current and the emitter current. Alpha is, often in the range of kind of 0.99. It's kind of a typical value, 0.98 maybe. Okay, so in terms of writing emitter current in with respect to our base to emitter voltage, we remember that our collector current was the saturation current times e to the VBE over VT. My V here should technically be lowercase. This divided by alpha will give me my emitter current. Okay, this term alpha here, as will become clear, the reason will become clear later, but alpha is known as the common base current gain, base current gain. Okay. In terms of relating the collector current to the base, we use the Greek letter beta to define the relationship between the collector current and the base current. This is a parameter that's often given in data sheets, written in terms of our base to emitter voltage, the base current, of course, being the collector current divided by beta. Okay, and here again, common values of beta are, often in the range of 100 to 300 are typical values, where beta, again, which will become clear later on, beta is known as the common emitter current gain. Okay. We can also relate alpha to beta. Alpha can be found as beta divided by beta plus 1, although this is approximately equal to 1. And this comes from the fact that our emitter current is approximately equal to our collector current, or we can solve for beta from alpha. If we know alpha, beta is equal to alpha over 1 minus alpha. Okay, this value is much larger than 1, and this originates from the fact that our base current is much smaller than our collector current. Okay, so all of these equations are going to be extremely helpful and required going forward as we start to analyze transistor circuits and need to calculate the relationship between the various currents of the device. Okay, so we'll end it there for this lecture, and the next lecture we will dig into what the transistor looks like and how it behaves in saturation mode.